Before designing the bridge members, we gotta identify its geometry first. This video shows the computation of bridge length. Welcome to Bridge Engineering. Say we are to construct a simple span bridge crossing a river. The river spans 20 meters. Logically, the bridge we need to build has a length computed as the clear span or the river width plus some allowances which we are to discuss later. It matters less when the bridge is longer than needed, but the AASHTO has adopted minimum support length. This stipulation aims to ensure the girder has enough bearing seat on the abutments if we are talking about simple span bridges, or on piers for continuous bridges. This length is computed to define safety during load transfer. It is also for construction tolerances, and again, safety with thermal movement. The typical minimum bearing length of the bridge can be computed using n as greater than or equal to 0.06 L plus 100 mm, where n is the minimum support length or the allowance at one end in mm. L is the span length or the river width for simple span bridges. For the river presented earlier, having 20 meters width, n is then computed as 0.06 of 20,000 mm, then add 100 mm to give 1300 mm. This is n for each support. There is also the empirical formula provided by New York Department of Transportation with common practices of AASHTO. And this time is the summation of 8, 0.02 of L, and 0.08 of H, multiplied by the skew factor. For this equation, N is still the minimum support length but in inches. L is the span length in feet. H is the average height of supporting columns, also given in feet. With different bridge types, the typical H values are the following. Slab bridge usually takes 0.6 to 1 meter. For pre-stressed girder bridge, H is 1.2 to 2.5. And for steel girder bridge, H is taken as 1.5 to 3 meters. Though H is based most of the time with the spans of bridges. That is, for single span H is around L over 12 to L upon 18 to L over 20. L divided by 12 is used for conservative design, and the range L upon 18 to 20 are for efficient systems. For continuous span bridges, H is then computed as L over 18 or L over 25 to L over 30. The first is for conservative design, and the range after is for optimized design. The last parameter in the equation is the skew factor. This accounts for the increase in load distribution effects due to the bridge skew angle. The skew factor depends on the angle, where from 0 to 10 degrees, the factor is 1, until 45 degrees with a factor of 1.35. If the skew angle is more than 45 degrees, a more refined analysis is necessary to look for the skew factor. Now back to the example. With a simple span bridge, H is considered as 0, then the skew factor for a straight bridge is 1. N is then computed as 8 plus 0.02 by 20 meters, converted into feet using 3.28 feet per meter. Then add 0.08 by H of 0. Then the skew factor is 1. The allowance is then computed as 9.31 inches. And again, this is per support. Since the problem uses metric, we convert 9.31 into meters, which is 0.236 meters or rounded to 24 centimeters. With the two equations used for a AASHTO minimum support length, what do we use? The equation provided by NY dot is for the seat length requirement based on stability. This is for short spans and non-seismic regions. While the shorter equation includes allowance for seismic restraint, tolerances, and displacement demands. This is a more conservative approach and is more used in modern LRFD practice, especially in seismic areas. To make the comparison short, the first equation is for basic bearing. The latter equation is for safety and seismic response. In the computation of bridge length, always use the larger value. Now back to the example. With the allowance of 1300 mm adopted for each support, the total length is then the clear span plus twice of n. That is 20 meters plus twice of 1.3 meters, which gives the length of the bridge as 22.6 meters.